8 is going to continue on with the continuous variables, using the standard normal chart, all that stuff. The only difference is now, instead of just random data, we're going to have means, okay? So we'll have means as our data, and it's a little bit different, and we'll talk about how that happens, okay? So 8.1 is called the distribution of the sample mean. 8.2 will be the distribution of the sample proportion, which we'll introduce on Wednesday. So it says, often the population is too large to perform a census. So what do? We do the next best thing. If we can't ask anyone, what do? We take a sample. If we can't ask everyone, we can at least take a sample. Okay? So the question always arises, how do the results of the sample we take apply to our population? So that's that theoretical inferential statistics that we'll talk about in chapter 9 and 10. The question is, when we take a sample, how close is that sample mean to the population mean? Is it close or not? And how close are the sample standard deviations? This is called statistical inference. And like I said, the inferential statistics that we're going to talk about will be in chapter 9 and 10. So that will be after test 3. In theory, what we want to do is we want to be able to use our sample mean, and don't forget the symbols, because this is where it's going to kind of all come back to us, this chapter. The sample mean symbol is still x bar, so that's nothing new, all right? And we want to use that sample mean to help us estimate the population mean, mu. How does it work? So let's look at objective 1. Say we want to estimate the average GPA of all LC students. We could proceed as follows. We could randomly select 100 LC students, compute the sample mean, and use that as our estimate. But say you're lazy. You're like, I don't want to go ask 100 LC students. So you have friends that will help you out. Don't you guys agree that if I get 10 friends who ask 10 people, that's a sample of 100? You guys agree with that? So the question is, if they ask 10 people and find their mean, and you ask 10 people and find their mean, how does it all come back together? And what's neat is it's the same. So whether you take an average of 100 things or average 10 averages, they're all going to be the same, all right? So what we want to realize is we would come back and we'd have a sample mean for my first friend, we'd have a sample mean for my second friend, we'd have a sample mean for my third friend. So my sample mean is now the random variable, okay? So x bar is now the random variable. What does that mean? That means instead of just putting 100 different GPAs into my list 1 and hitting one variable stats, I would put 10 different averages into my list 1 and hit one variable stats. So I'm putting averages in instead of just normal GPAs, all right? So what do we know about the sample mean then? We could come up with its mean. So the sample mean has a mean because I could put my 10 averages in my list 1. I could hit one variable stats and the average would come up for that. And it would also have a sigma pop up. So it also has a standard deviation as well. And guess what? If you have an average and you have a standard deviation and you're approximately normal, then you can have your own probability distribution. All right, so what we're going to find in 6.1, guys, is that everything we put into list 1, what we're averaging are sample averages, and then in 8.2, it's going to be the same idea, but it's going to be proportion averages, all right? So this is called, it's the biggest, wordiest title ever, okay? Are you ready for it? It's called the sampling distribution of the sample mean. The sampling distribution of the sample mean. Whew, it's a mouthful. The sampling distribution of the sample mean. Why is it called the sampling distribution? Because I'm only taking samples. But what am I putting into my list 1? I'm putting in sample means, okay? So on Wednesday when we do 8.2, that title is the sampling distribution of the sample proportion. Because again, I'm sampling, so that's why it's called the sampling distribution. But what am I putting into my list 1? I'm putting in a bunch of proportions. All right, it says when we use the sample mean to estimate the population mean, we're using a parameter, we're estimating a parameter, remember that goes with population, with a random variable, okay? So what we have to keep in mind is we need to know these 3 things. We need to know the size of our sample. Do you guys remember the symbol for sample size? Nope. Little n, you got it. Do we remember the symbol for a population mean? Nope, a sample mean. Nope. Mu. And do we remember the symbol for population standard deviation? Sigma, okay? So that's what we're going to have to keep in mind. We're going to have to be told what the population mean is, so we can still do the minus mu, okay? We're going to have to be told the standard deviation, so we can still divide by sigma. But what's going to be new now is we're going to have a sample size, when before we didn't. We just asked one person, okay? So what it has on the next page is basically kind of showing you that if you start off being normal, and you take samples, you're still normal. So do you guys agree both the top and bottom are normal curves where it's higher in the middle and smaller on the left and right? But what we want to realize, and this is like the key thing, and I have an activity if we need to do it to kind of pinpoint what's happening. But do you guys agree when I start averaging, we start going towards the middle? What do I mean by that? Think about you guys in this class right now. Think about your test scores. Some people are scoring 98 and some people are scoring 68. But what happens when I average a 98 with a 68? What happens with a 98 and 68 if I average them? How do you average? Add and divide by 2. What's going to come to that number? They're going to kind of come more to the middle, right? So they'll be 82 or something like that. So what we have to realize is when we start averaging a bunch of things, we're not going to be as extreme. We're not going to be as spread out. So all this is showing you is if you average a sample of size 5, look what the range is. It's nearly 35 to 75. But if you ask 15 people and average all of their scores, then you only range from like 45 to 65. So in a nutshell, what do we want to show? The larger the sample, the smaller the spread. So standard deviation is smaller. Okay? The larger the sample, the smaller the spread. And like I said, this is brand new to you. We haven't done anything yet, but I want you to realize is now instead of asking one person what their test score is, I'm going to ask 10 people what their test score is and average it. And by averaging it, it's not going to be as extreme to the left or right. It's going to be more towards the middle. So the larger we take the sample, the smaller the spread will be. All right? So here I asked 5 people and we spread from 35 to 75. Here I asked 15 people and the spread was only 45 to 65. Because all the highs start canceling out with the lows. We kind of start coming to the middle. All right? So if you got that down, go ahead and flip it to the top of page 3, guys. There's a lot of words, blah, blah, blah. But I'm going to try to highlight the key things, okay? Highlight and circle the key things on page 3. It says, if we know that the population has a normal distribution, so if the population is normal, guys, the sampling distribution is also normal. Basically, again, if we're starting with normal data, if we start taking averages, those averages are still going to be normal, okay? This is kind of important. It's kind of just written in words. Further down here, we'll write it more in formula. We know, in fact, that the sampling distribution will not only be normal, but the mean will be equal to their original mean. And that's what I mentioned. Whether I asked 100 people their GPA and took that average all at once, or whether I asked 10 people 10 times, that average is going to be the same. But what's going to happen to the standard deviation? We just wrote it right here. What happens to the standard deviation? It's going to get smaller, okay? Because the highs and the lows are going to start canceling each other out. So it says we'll have a standard deviation less than the standard deviation of the population, okay? So instead of putting raw data, meaning your individual GPA scores, I would start averaging them. So I might take hers and average it with Jake's, and we'd have more of a middle ground. And I take hers and average it with Grace, and we have more of a middle ground. So our standard deviation is going to be less, and here in a second we'll find out exactly how much less, all right? And this is all it's saying, like, it's trying to tell you what I just said in words. Why did we have a smaller standard deviation? Well, the population standard deviation measures the distance between an individual and the mean. And the standard deviation, the sample mean, is measuring the distance between the sample mean and the mean. So that should be a smaller distance, right? It makes sense that if we estimate it and it's more accurate, then we're going to have a smaller standard deviation, all right? So the next thing is the law of large numbers. And he is written in a more complicated way than it should be, I think. But anyway, the law of large numbers says that As we add more observations to the sample, i.e. n gets larger, the difference between the sample mean x bar and the population mean mu approaches 0. All it's saying is the more people you ask, the more accurate you're going to be, right? If I want to estimate Elsie's GPA, should I just use Taylor's GPA? No. Should I even use the average of your guys' GPA? Probably not. I probably need to expand it to more classes to get an idea. And that's all it's saying is her GPA is probably way higher than Lewis and Clark's average GPA. But then if I ask you guys might get it closer to it. And if I ask all 100 of my students this semester, we might get closer to that GPA, okay? So the larger your N, the closer your sample is to your population, all right? The next thing, guys, again, it's just kind of getting into sigma. When we find the standard deviation of the sampling distribution, it's actually called the standard error. I will never, don't tell on me, but I will never refer to it as standard error. Okay? The standard error is just a way to say it's the standard deviation of the sampling mean. But you do want this. So highlight, circle it, whatever you need to do. We knew it was going to be smaller. How much smaller did we know it was going to be? We didn't. But somebody was able to calculate that from now on, guys, when we go to calculate our new standard deviation, we're going to take the initial standard deviation of the population, but then divide it by the square root of our sample size. Okay? So let's go ahead. I'm going to try to, this is just, again, kind of wordy. Just like now we know it's normal, we know the mean, we know our standard deviation, we can do calculations now. So let's look at down here real quick to make sure we feel comfortable. All right. So it says if the random variable x has a normal distribution, so this is our normal everyday guy, and the mean's 20, what can we label that? That is mu. Okay? And the standard deviation is 12. How can we label that? That is sigma. So it's nothing new so far, guys. But what we're going to start doing is instead of choosing one person, we now are going to choose 4 people. How does that change my mean? It says the sample mean will have a normal distribution with a mean of what and a standard deviation. Way up here, what do we say about the means? The means are equal, right? So down here, when they said the mean was 20, guess what the mean still is when I take a sample of 4? 20. I don't do anything. The means do not change. The means do not change, all right? But what will the standard deviation be? Well, the standard deviation will get smaller by using this formula. Okay, so off to the side, let's just do that formula. What was our initial standard deviation they gave us? 12, and we're going to divide by the square root of our sample. What's our sample size? 4. What's the square root of 4? 2. So what's 12 divided by 2? 6, okay? So back in the day, the GPA used to be 12 when I asked one person. But now when I ask a sample of 4 and average their values, my standard deviation is only 6. It's not as spread out, okay? It's more compact. The second one's the exact same idea. Now I'm asking 9 people. What's the sample mean still going to be? 20. Your mean does not change. Your mean does not change. But your standard deviation will, again, by using this formula up here. What was your original standard deviation? 12. Divided by your square root of your sample size? 9. What's the square root of 9? 3. So what's 12 divided by 3? 4. And we could keep going. I could take a sample of size 16. What would my standard deviation be? Well, what's the square root of 16? 4. What's 12 divided by 4? 3. And you could just keep going and going and going. So, in a nutshell, what's the only thing you need to take in for 8.1 is that instead of asking one person, we're going to ask multiple people, okay? And we're going to use their average and their standard deviation, but we're going to do exactly what we did in 7.2, okay? So when you flip the page over, I left it blank, which is kind of risky, okay? Because this is the key formula. In order to do this, what we're going to have, we're going to kind of have a little line going on. We're going to have z equals x bar minus mu of x bar over sigma of x bar. And that looks kind of scary, but I'm going to talk about each of those, okay? So in order to find the z-score for the means, our random variables are no longer just everyday individual items, they're sample means now. Remember, I'm going to ask 10 people 10 times. So that's my sample mean, minus, that's still the population mean, and that's still the standard deviation mean. But what is this equal to, guys? What did we say the population mean was? It was equal to the original. So this is just minus mu. Yeah. Are you guys okay? Okay. So, what'd you say? Debatable. I'm not going to say 100%. Okay. So, guys, notice how we're still just trying to do x minus mu over sigma, right? The only thing is now, instead of our variable being x, individual data, it's mean. So that's why there's x bars there, okay? So we're going to take a sample average and subtract the population mean and divide it by the standard deviation. But all I'm saying is we know what the population mean is. It's the original mean. And then what do we know about the standard deviation? What is it? Sigma over root n. How you do this on MyMathLab is totally up to you. I like to just do it all at once. I like to keep my z-score formula the same. My individual minus my population mean divided by my standard deviation. If my n's greater than 1, I know I can put something in here. What MyMathLab does, though, MyMathLab, and I'll try to kind of match MyMathLab, a lot of times they'll ask you what is mu, and you just steal it, and what is sigma, and we put it in there. Okay, so let's see what's going on. Let's read this problem and see if I can make this formula make sense to you. It says the average room and board expenses per year at a college is $58.50. What can I label that still as? Mu. Suppose 9 students are selected. That is what's new. What can I label 9 as? N. And if you go back to any problem in Chapter 7, you're selecting a student. So it was a sample size, all right? What's the probability that their average expenses for room and board is less than $61.80? So that's going to be x bar. Assume your x is normally distributed with a standard deviation of 1125. What can I label that with? Sigma. So the only difference we're going to do from Chapter 7 to Chapter 8 is instead of dividing by sigma, you divide by sigma over the square root of n. It's the only difference. You still use that x, that individual value in front. You still subtract the mean that they told you in the beginning, and you still divide by your standard deviation. It's just your standard deviation divided by n, okay? So let's draw the normal curve. What's going on? And this is a very old problem because room and board's way more than this. This is probably for a semester, okay? When you draw just a simple normal curve, it's the everyday situation, which was room and board. Who goes in the middle? 58.50. But now I'm going to ask 9 people, say, what's your room and board? What's your room and board? What's your room and board? And go around 9 times and take their average. And I want to know the probability that their average is less than 6180. Where's 6180 on this chart? On what side? Right, and does it matter really where? No, I'm not going to be picking and have my ruler out, but it's just somewhere over here. So just make sure you get it on the right side. And then which direction am I going to shade since it's less than? To the left. So right off the bat, without even calculating, you can tell me if my probability is going to be less than 50% or more than 50%. Right? What is it going to be? Less than 50% or more than 50%? More than. Why? I'm shading more than half the graph, right? 58.50 would be half the graph, but I'm over here and shading more than it. So we know we should get an answer more than 50%. All right. Convert the values of x to z. So how MyMathLab does it is I think they say, well, what is mu of x bar and what is sigma of x bar? So early in the problem, they just ask you, well, what is now your mean for your sampling average? And what do we know about the means? The means don't change. The mean is just mu that you labeled, which in this case is what? 58.50. What is sigma of x bar, though? That formula that we circled on the page 3, it's sigma over root n. So in this case, we do have to do something. We have to take sigma, which is 1125, and divide by the square root of our sample size, which is 9. What do you guys get when you take 1125 divided by 3? 375. Okay, that is rare. Just FYI, you rarely get this perfect little beautiful number of 375, okay? So if it's ugly and it has decimals that go on forever, be as accurate as possible. Use 4 or 5 decimals, okay? So guess what we can do now? We can do our z formula, and we can just use this formula. X minus mu over sigma. Because what did we say the mu was? We said the mu stayed the same as 58.50. What did we say our new standard deviation was? We said, well, instead of a spread of 1125, it's only a spread of 375 now, okay? So z equals x bar minus mu of x bar over sigma of x bar, all right? What was x bar? That's always the part in the question, right? So we asked 9 people, what's the probability that their average is less than 6180? So that's always the part of the question. minus the mean, but you guys have already told my math lab what the mean was in step A, okay? What did we say the mean was? We said the mean stayed the same as 5850. Divided by our standard deviation, and what did we calculate our new standard deviation to be? 375. This right here is the only new thing we do in 8.1. Instead of asking one person, which is pretty extreme, we're asking 9 and averaging them. So the standard deviation is going to be smaller. So what do you guys get for a z-score rounded to 2 decimal places? 0.88. At that point, everything's exactly the same. It's 0.88, so we're going to draw our standard normal curve. Do you guys have to draw curves? No, I'm just trying to show you how everything relates. A standard normal curve is always centered at what? 0. This value of 6180 was off to the right of the mean. Well, notice where our z-score is. It's to the right of the mean. Good. We know we did our math correctly. But we don't really care about steps 1 and 3. We care about steps 2 and 4. What is my new z-score, and how did I use that to find area so I can answer my question? Okay. You look up 0.88 on your chart. What do you guys find? I don't even have my chart. So we're going to go down to 0.8 and scroll over to the second to last column. 8106. Does that look right? All right. So in my math lab, you would just type this. But again, I kind of, oops, you can't see it. In my math lab, you would just type this on the test. You would just circle that. But again, I kind of like to write a couple of different ways of how we can interpret this. This means we found the probability that the sample mean was less than 6180. Okay? The probability that those 9 kids had a room and board less than 6180. We don't have a chart about room and board, so what did we have to do? We had to change it to a z-score of less than 88, right? And that was the 8106. So what does that mean in words? It means if we took 1,000 random samples of size 9, I'm going to write that. If we took, because I think this is always on those problems, if we took 1,000 samples of size n equals 9, about 811 of them would have an average room and board expense of 6180 or less. And once you write that down, go back and ask, where did I get the 811? If we took 1,000 samples of size 9, about 811 of those 1,000 samples would have an average room and board expense of 6180 or less, I should write on there. Does anybody see where the 811 came from? Where did it come from, Spencer, since you're shaking your head? You just multiply by 1,000, right? Remember, this percent, this area represents proportion, right? So 8106, right? So all you have to do is take the 0.8106 times however large a sample you're taking, right? So 8106 times 1,000 would move that decimal over to 810.6, which would round up to 811, okay? Do you guys see what the only difference is right here? Yes? No? Do you understand why? Like, do we need to do the activity to prove it? I mean, basically in a nutshell, instead of going around and asking each of your guys' weights or each of your guys' GPAs and put it into my list 1, I would average them first and put that average in my list 1, okay? So my random data is just averages now. And since they're averages, they don't vary as much, okay? So the standard deviation is just a little bit smaller, and that formula is just sigma over root n. Only difference. The shading to the left, the shading to the right, all that's the same. All right, so the only thing that's kind of different on 5, which wouldn't make it a difference at how you approach the problem, because I would not be mean and give you one that wouldn't work, is the only reason why we can do all this jazz is because your x is normally distributed. But if you look at this one, nowhere in here does it say x is normally distributed, so you're like, what am I supposed to do? Well, remember, you can do 7.3. You could throw your data into your calculator and see if it's approximately linear, then it's approximately normal. Or we have this theorem called the central limit theorem. Central limit theorem. oops, can you see that? The central limit theorem is probably one of the most important theorems in stats. Like, I had to prove it with calculus, and it was so stupid, because I'm like, somebody's already proved it. Like, why do we have to do this? But anyway, the central limit theorem is a very nice theorem, because it says regardless of the shape of your distribution. So whether your distribution started left skewed, right skewed, uniform, it didn't matter. As your sampling distribution, as n increases, your sampling distribution becomes approximately normal. So say I only ask 10 people and I have a left skewed thing, well then when I ask 100 people, it might go from left skewed to normal. And then I could use all these rules we were using before. The question is, how big does n need to be? Like, what's enough? Is 10 enough? Is 15 enough? And that's right here. I'm going to star it because it's something that you kind of want to keep in mind. As a rule of thumb, as long as your sample is 30 or more, guys, you do not have to have a normal distribution, okay? It can be left skewed initially, but if you ask 30 or more in your sample size, then it's going to be approximately normal, okay? So this kind of goes hand in hand. As n increases, you get approximately normal. The question is, how big does n need to be? It needs to be 30 or higher. So let's read this example. It says, on average, drivers spend 25 minutes a day behind the wheel. What can we label what can we label 25 with? Mu, sorry, I gave that to you. You randomly select 50 drivers. What can I label 50 with? N. What's the probability that the mean time driving is between 24.7 and 25.5 minutes a day if the population standard deviation is 1.5? What can I label 1.5 with? Sigma. So notice nowhere in here do they say assume x is normal, right? But what do you notice about our n? It's 50, which is greater than 30, okay? So the reason why I'm pointing this out is because it is important, but on a test, guys, I'm not going to give you this problem and only have a sample size of 15, and you do all this work, and I'm like, nope, it wasn't normal, you're screwed, minus 5 points, you know, that kind of thing. But kind of keep it in mind, because my math lab will ask you, they're like, here's the scenario, is it approximately normal? You'll say yes, because my sample size is large enough. Or no, my sample size needs to be larger, or whatever you need to do, okay? So let's go ahead and draw our normal curve, guys. Remember, your normal curve is your everyday real life values. So the mean of 25 minutes is going to be right there in the middle. And we care about this is so weird, 24.7 to 25.5. So 0.3 of a minute to the left, and half a minute to the right. So it doesn't seem like a very big range. How many of you guys easily spend more than 25 minutes a day behind the wheel? Right? I mean, just getting here one way, some of us are spending more than 25 minutes. But we have to keep in mind, guys, we have people in New York or Chicago that are just commuting via bus, right? So we have to keep in mind that we have these zeros canceling out these, I spend 70 minutes behind the wheel just to and from work, you know, that kind of idea. So what we have to do is we have to convert our x values to z-scores. I didn't leave a whole lot of room, I apologize. So let's go over here and write what's going to be our new mu of x bar. Well, I say new, but is it really new? No, your mean doesn't change. Whatever mean they tell you, guys, it's just going to be mu that they told you, which was 25 minutes. What is going to be our new sigma of x bar? What do we have to do? Sigma divided by what? Square root of n. That's the only new guy, okay? So instead of asking one person, I'm asking 50 people and finding their averages. So what was our sigma? 1.5, and we have to divide by the square root of 50. And this is what I'm talking about, guys. We're going to get something that's really, really crazy decimal. To 5 decimal points, you get 0.21213. Does that look right? So instead of give or take a minute and a half for our standard deviation, we're give or take, like, what is that? A fifth, so like 12 seconds, give or take, okay? Because we're asking 50 drivers at a time now, which 50 drivers at a time is a lot more accurate than 1% at a time, all right? So how do we convert our x values to z's? Well, we have 2 of them up here, all right? This is x bar and this is x bar. We're going to do z equals x bar minus mu of x bar over sigma of x bar twice. Z equals x bar minus mu of x bar over sigma of x bar twice. Okay, what will stay the same? The mean, okay? So the 25-minute mean is going to be the back number for both.